All right, so now we're going to look at verifying trig equations. So verify means the equation's already solved. Okay, so we're not solving it to see what the answer is. It's the steps that we're going to use to get the answer. You can work on one side of the equation. You're not allowed to move things across the equal sign like you can in a regular algebra problem. Like you can't subtract like cosine x over to the other side. You can't divide both sides by some trig function. You can only work on one side. So it's really the same thing as what we've been doing as far as simplifying the trig expressions down. The only difference now is I already tell you what the answer is. All right, I'm telling you what the answer is. You're just going to show me the steps to get that answer. All right. So before we do that, I want you to fill in each of these identities. All right, so the reciprocal identities, the quotient identities, and the Pythagorean identities. So see how many of these you can do from memory. Ready, go. All right, so on number one, I need you to change tangent to cotangent. Else it's not going to work out. All right, so when we're verifying trig equations, remember, we're only allowed to work on one side, and so I'm going to have you always work on the left side. So we're always going to make the left side turn into the right side. So basically, there's this barrier here, okay, where the equal sign is, and you're not allowed to cross it. Can't move things across it. All right, so using our different reciprocal identities, Pythagorean identities, quotient identities, we want to change things so we can simplify it to the right side. So secant we can change to 1 over cosine. All right, and then cotangent we can change to cosine over sine. Now when we basically you're showing your steps on how you're getting this to simplify to cosecant x. So you're going to work down, okay? So you always want to work vertically instead of across as much as you can. Anyway. All right, so here we can cross cancel, so we can show that step that we cross canceled. And then we multiply it across, so we bring down the 1 over sine x. And then just kind of keep an eye on what you're trying to get it to be. You're trying to get it to cosecant x. Well, 1 over sine x is cosecant x, right? And that equals cosecant x. And we put a little check mark to show that we proved, okay, this is a proof, that the left side is equal to the right side, right? So kind of like in geometry where you did 2-column proofs, so you had statements on one side, reasons on the other. It basically works the same way, except you're not providing the reasons, you're just basically providing the statements. As you get higher in math, if you were to take like calculus, they do calculus proofs, and they're just a little bit different where they just write out the steps in sentences instead. Okay, or they use this 2-column idea where you're just working on one side. And then as you get higher in math, they will allow you to work on one side and the other side, the right side, and you're basically working on both sides because the problems are really complicated. And then once you get the left side and the right side to equal each other, you proved it. All right. But these problems aren't going to be that difficult, so always work on the left side though. All right. Now on number 2, cosine x minus cosine x times sine squared x. All right, so everything's already in sines and cosines. I can't combine anything together, okay? But I got to get it to cosine cubed. So one technique that we can use, we already saw this in the simplifying 10.1, is we could factor a GCF out, all right? And so what's the GCF? Cosine x, yeah. So let's go ahead and factor a cosine x out. And then we're left with 1 minus sine squared. Now, 1 minus sine squared is a Pythagorean identity, which is equal to what? Cosine squared, right? And now we have cosine x times cosine squared x, which is cosine cubed x. Right? And so we just proved the left side is equal to the right side. All right, number 3, 1 plus sine x over cosine x, and we need it to be secant x plus tangent x. Now, we don't have a Pythagorean identity because we don't have any squares. All right, so you can't change like 1 plus sine x to anything. So what we're going to do on this problem, and we saw it the other day, is we want to split this up into 2 fractions. All right, so we want that cosine x to go underneath both terms as 2 separate fractions. So that's what we're going to do. So we have 1 over cosine x plus sine x over cosine x. Now 1 over cosine x is secant x. And sine x over cosine x is tangent x. And we just proved it. All right, now number 4, you actually have 2 methods that you can use. Either look for a Pythagorean identity, because you have a square and there's a -1 there, so it's probably a Pythagorean identity. You could also split this up into 2 fractions like we did on number 3. So you have 2 different methods that you can use. If you use the Pythagorean identity, then just be prepared to use complex fractions because that's what's going to happen. If you split it up into 2 fractions, then you won't have to. So it's up to you which method you like. But one thing don't do, and I noticed some of you guys do this on the homework, because you had a problem similar to this, people want to just cancel these out. You can't do that, because this is a binomial, all right? And you can't cancel part of a binomial out. So not cancel these out. Split it, okay? This is a pi. Cancel them out. You can't just cancel them out. All right, so if you use splitting these up, then it's cosecant squared x over cosecant squared x minus 1 over cosecant squared x. All right, now that cancels out, meaning it cancels out to 1, not 0. And then 1 over cosecant squared is sine squared. And 1 minus sine squared is a Pythagorean identity, which is cosine squared. And that's what I'm trying to prove. All right, so don't be afraid of fractions. Yes? Where did the 1 minus sine squared come in? Well, cosecant divided by cosecant is 1. Minus 1 over cosecant squared is sine squared. That's from the reciprocal identity. 1 over sine is cosecant, or 1 over cosecant is sine squared. So that's where that is. This is a Pythagorean identity from the top. Okay. So we're working down. All right, now you could. Did anybody try doing this using the Pythagorean identity at the beginning? All right, you can. You can change everything to sines and cosines. Right? So cosecant squared x minus 1 is what? If we just change the top. What's cosecant squared x minus 1? Yeah, I'm showing you another method. Okay? Cotangent squared. Look at your Pythagorean identity. All right, then I can change everything to sines and cosines. So cotangent squared, you could change that to cosine squared over sine squared. That's being divided by 1 over sine squared. All right, so you have a complex fraction, cosine squared x over sine squared x times the reciprocal, which then you can cross out the sine squares, and you get cosine squared equals cosine squared. So it's just a different method, and it still works. So it's up to you which method you like. It's up to you to figure out which one works though. All right, then the last one, number 5. All right, so we have sine x times tangent x plus cosine x. We're trying to get it to equal secant x. There's no GCF that you can factor out, nothing in common. So here you want to change everything to sines and cosines. So we've changed tangent to sine over cosine. Now I can multiply sine x over 1 times sine x over cosine x. That becomes sine squared x over cosine x plus cosine x over 1. All right, so now I want to add these two fractions together, but the denominators are different. So to get them the same, I can multiply this fraction by cosine x. All right, so now I have sine squared x over cosine x plus cosine squared x over cosine x. Now I can write one single fraction. Put cosine x on the bottom. And then I have sine squared x plus cosine squared x on top. Now sine squared x plus cosine squared x is a Pythagorean identity. That equals 1. 1 over cosine is secant, which is what I'm trying to prove.